Hello, section 2.4 mathematical induction. Okay, this is a nice thing. This is how you would prove an infinite number of statements that are sort of lined up in a sequence, and this we'll use over and over and over again. So you want to understand this completely. Well, completely maybe is an over-exaggeration. But anyway, so the idea is that you have an infinite number of statements. So imagine each one of these boxes represents a proposition that could either be true or false. So the idea of mathematical induction is that you show that the first one, you make a proof that the first one is true. Now, that's true. And then the idea is that you assume that that is sort of, so then you might think, well, let's prove the second one is true. Well, no, what we do is well, once we prove the first one is true, then you see we could use the fact that the first one's true to prove the second one is true. All right, so essentially what we're going to write down is a proof of how to go from assuming that a particular one is true. So imagine this is true, maybe this is true, this is true, this is true. And suppose we made it up to proving the fifth one is true. Then what we will do is we will assume, say that the fifth statement is true, right? And then we will use that to prove that the sixth statement is true. Now, if we were to do that in general, what we would be doing is we would be doing this. We assume that for all n, if block n is marked, in other words, as true, then block n plus 1 is also marked. So this is really what we're going to be proving, and that is we're going to show that we can prove that the n plus first block is marked as true, just assuming that block n is marked as true. And this gives us the mechanism by which we can then conclude that they are all true. Okay, so think about that. I think you will agree. Okay, here's let's look at an example, I guess here. Okay, here's a nice example. So there's this formula that we would like to conclude to calculate this thing called S sub n. And what we'd like to show is that this number, if you add up the first n entries, integers, that is, positive, that we get the same as if we just write down this formula, right? N times n plus 1 over 2. And what you can see is that this represents a sequence of statements. S1 is 1, S2 is 3, 3 is 6, right? And et cetera, et cetera. So what we will do is that is the following. So we must show that for all n, if the equation n is true, then equation n plus 1 is also true. Okay, so we're going to assume, so watch how this works. So we're going to assume that this is correct. That is, that if I can write down 1 plus 2 plus 3 plus 4 plus 5 all the way up to n is equal to n times n plus 1 over 2. And what we want to do is prove that, in fact, Sn plus 1 is actually equal to n plus 1 times n plus 2 over 2. Okay, to be true. Okay, so then we'll say, well, let's take a look at Sn plus 1. So according to the definition, it's basically adding up the first n plus 1 positive integers. And so we note that Sn is contained within Sn plus 1, right? Sn plus 1 is actually equal to that. But notice the first n, this part right here, that is Sn. So we replace it with Sn. So then we can see that S sub n plus 1 is S sub n plus 1. And then essentially going through and just writing down what that is, we do a little bit of arithmetic or algebra, I guess, here, right? Just this is from here, then you simplify it and you come up with that. So lo and behold, we have our result that S sub n plus 1 in fact is equal to that, based upon the assumption that Sn was equal to this. Okay, and so therefore that argument right there is enough to prove that Sn, the formula for Sn is correct. Okay, so here's what we call the principle of mathematical induction, and it's a method of proof that we will use many times. Here we go. Suppose that we have a propositional function S sub n, whose domain of discourse is the set of positive integers, just the set of positive integers for now. Suppose that S1 is true. And then let's say that for all n greater than or equal to 1, we want to prove that if Sn is true, then Sn plus 1 is true. Then Sn is true for every positive integer. So this is the idea that if we can prove these two things, that guarantees that Sn is true for every positive integer. And how you want to think of that is that, okay, if we knew S1 was true, then we could use the argument here to prove that S2 is true, and then we could repeat that over and over and over an infinite number of times. And so there does not exist any integer, say j, such that S of j, right, S of j is false, because if it were, that would make S of j minus 1 would have to be false too, and you can go backwards basically and get to 0. And so, okay, here's a nice definition that we'll be using through the course quite a bit. The idea of factorial. So n factorial is defined to be, well, it's 1 if n is 0, and then you just multiply all the numbers less than or equal to n together to get n factorial. Here's some examples. All right, let's go through this example. Let's use induction to show that n factorial is bigger than or equal to 2 to the n minus 1. All right, so the basic step, that's when n equals 1, we must prove the formula is correct when n equals 1. So to do this, it's a simple calculation to show that 1 factorial is 1, and in fact that is greater than or equal to 2 to the 1 minus 1, which is 1. Okay, now here's condition, what they call 2.48. So they're talking about this condition right here. And they, sorry, referred to as the inductive step, okay? So we assume that this inequality is true for some n greater than or equal to 1. That is, we assume that this is correct. And now, or in other words, is true. Now what we must prove, so we must now prove that the inequality is true for n plus 1. That is, we must prove that this is correct. Okay, so how do we do that? Here comes the proof. So you just write down the equation. In this case, n plus 1 factorial is equal to n plus 1 times n factorial. Now, we know from our assumption here that n factorial is actually larger than or equal to 2 to the n plus 1. So that allows us to write this inequality down. And now we know that n plus 1 is actually, wait, what's happening here? Oh, here we go. Now watch this. Now since n plus 1 is greater than or equal to 2, remember n is assumed to be greater than or equal to 1, then we can replace this n plus 1 by the smaller number of 2, okay, and preserve the sense of the inequality. But just doing the calculation there, we get 2 to the n, and therefore that completes the proof. Okay, let me do another one. This one is, okay, I don't want to actually go through the geometric sum. Go through all of these when you read the book, of course, but I wanted to go through one that is has this one. I want to prove this theorem actually, and yeah, we'll use induction to prove this theorem. And this is kind of an amazingly important theorem and very interesting. So the theorem is that if the number of elements inside of X is equal to n, then the number of subsets of the set X, the number of subsets of the set X is equal to 2 to the n for all n greater than or equal to 0. Okay? So here Well, here we're starting we can start the inductive proof on n. The basic step is when we have n is equal to 0. That's the starting point. We can start with 1 or 0, but whatever number we like, but we have to use the basic step. It has to be the proof of the very first element in the set in the ordering of the that has the same ordering as the positive integers. Okay, here we go. So if n is equal to 0, then X is the empty set, right? And the only subset of the empty set is the empty set itself. Thus, the power of that's correct. The number of elements in the power set is 1, which is 2 to the 0, which is equal to 2 to the n. So that's correct. Okay, now for the inductive step, let me step away and prove this portion of it right here. Okay. Well, let me outline the proof of it first. So we assume that this holds for all n, right? Holds for just for n, and let's let X be a set with n plus 1 elements. Okay. So here's what we do. So we choose an X inside of X, right? And here's our claim. We claim that exactly half of the subsets of X contain X. Well, let me take a little pause. I want to show you that. Hi, yes, I want to show you a proof of this one fact. What I would like to prove to help us in our proof that we're about to finish about these sets is that if I look at these two sets, they have the same size. Okay, so if you look, so what is this? I want to prove that A sub X, which is a set of all subsets B, where B is a subset of capital X, and X is not an element of B, and its complement, which is the set of all sets C, such that C is a subset of X, and X is an element of X. I want to show that they're the same size. And to do that, to show sets of the same size, I'm going to find a one-to-one and onto function between these two sets. And that is enough to line them up so that you can see there's exactly the same number of elements in each. And the function we're going to use to do that is f, which is going to map the sets that contain X into the sets that don't contain X in the following way. F of a set B is going to be just equal to B union the set X. Now, remember, B by assumption does not have X in it, so when we throw X in, this then becomes an element of our set, the complement of it, right? So F is 1-to-1. Why is it 1-to-1? Since if we know that we get the same image, B union X equals D union X, well then, let's see okay, since both B and D must come from the set A sub X, we know that X is not inside of B or D. So if you remove X, the only way that happens is if B equals D. And that shows it's 1-to-1. Now for onto, let C be an element of this set. Then if I consider the set C minus the element X, that is now an element of, this should be A sub X. Sorry, let me change that. All right, oops, try it again. Well, there should be a little X right there. For some reason, it's not corresponding, doing anything. Okay, so what does that mean? So F is onto, okay? Since if I take F applied to the set C minus little x, I get C. Okay, so that is why we can conclude that those two sets have the same size. Okay, we're back here. Okay, so we just showed that the set of sets that subsets of P of X that contains X is the same as a number of subsets of X that does not contain X. But if we look at if we let Y be that set of all elements, that Y be the subset of the collection of all sets that do not contain X, then we see that is a set that has just n elements because we've removed X from the set X to get it. Well, therefore, we know that the size of it is exactly the size right here is the size of the power set of X divided by 2, because half the elements in the power set of X are in that set. So therefore, multiplying both sides by 2, we get that the size of the power set of x is equal to 2 to the n plus 1, and that completes our inductive proof. So, okay, well, thank you. That's where I'm going to end our discussion in 2.47 for now. And let's see, is that correct? I believe that's correct. Yes. All right. Thank you very much.